The last part of thermochemistry that we're going to be concerning ourselves with are thermochemical equations, which are basically balanced equations with heat taken into account. So you can think of heat as either a reactant or a product. And which side we put the heat on will depend on whether it's endo or exothermic. So as I talk through the next couple of definitions, you might be thinking to yourself and say, self, if it's endothermic, would I put it as a reactant or a product? And if it's exothermic, would I put it as a reactant or a product? Heat, that is. Okay, so enthalpy is merely the fancy way of describing the heat content of a system, or the heat transfer that's taking place in a chemical system. Calorimetry is simply the study of the heat changes that take place in a chemical reaction or physical reaction. And a calorimeter is the object that we use to measure the heat flow in a system. Now, if you think about it, what would be the most important measuring tool in a calorimeter? And here's a basic calorimeter, and you can see that its most important part, other than the insulation, is the thermometer to measure the temperature changes as the heat is transferred. Okay, so in a chemical equation, the enthalpy changes for a reaction can be written as either a reactant or a product. So a minute ago, I asked you to ask yourself, if it's endothermic, would it be a reactant or a product? Now, if you remember, endothermic is energy is absorbed by the system, and the reactants have low energy. Okay, so as an endothermic reaction, the enthalpy changes can be considered as reactants. We put them on the reactant side since heat is absorbed. You have to add energy into the system. So here's a reaction where we have sodium bicarbonate, where 129 kilojoules is absorbed by the system, and it's chemically changing, decomposing into sodium carbonate and water and carbon dioxide. Okay, now if you remember back in the first part of the notes when we talked about endothermic reactions, we said that the delta H is positive, so we could then say there's 129 kilojoules of energy added into the system. That's how much more energy these products have than these reactants. Okay. Now, one sticking point, and this is, you knew it had to be coming with the balanced equation. This number is the amount of kilojoules per mole. But since there's a 2 in front of this reactant, then when you go to make any conversion, if you wanted to know how much energy is there in this product, then you have to take this coefficient into account. So if 15 grams of sodium hydrogen carbonate is decomposed, how much energy is absorbed? Okay, so 15 grams. What do you think we have to convert it to? Well, if this is 129 kilojoules per 2 moles, we don't know how many moles this is, so we have to convert the 15 grams of sodium bicarbonate to moles. So we take the 15 grams and we divide it by the FMG, and we get 0.179 moles. Now, this is the amount of energy, 129 kilojoules per 2 moles. So all we do then is say, I only have 0.179 moles, so I take the 0.179 moles and multiply it by the 129 kilojoules per 2 moles, and I get 11.5 kilojoules. Now keep in mind that a kilojoule is 1,000 joules. Okay. Now what about exothermic reactions? In an exothermic reaction, the enthalpy changes can be considered as products since heat is given off. So here we have calcium oxide reacting with water to form calcium hydroxide and 65.2 kilojoules of energy. So since energy is given off, it's being lost by the reactant. So this product has this much less energy than these reactants did. So the change in enthalpy, the delta H, is negative. Okay. So if 15 grams of the calcium oxide reacted with 100 mils of water, how much energy is given off? How do we do that? Oh yeah, this is 65.2 kilojoules per how many moles? There's no coefficient, so we assume it's 1. So it'd be 65.2 kilojoules per mole. So we have to convert 15 grams into moles. So we divide it by the formula mass, and we get 0.267 moles. And then we multiply it by the amount of energy per mole. So we get 17.4 kilojoules of energy released. Now, what if I wanted to know how much, how the temperature of the water changed? What would be the change in temperature of the water? What do you think we have to do? Think back to the last video. And I'm pausing for effect. That's right. We use the Q equals MC delta T. So we take the amount of energy that was given off by the calcium oxide, and it's going to be equal to the amount of energy absorbed by the water. 100 mils of water has a mass of 100 grams. Specific heat of water is 1 calorie per gram, or 4.186 joules per gram. And then the delta T is what we solve for. Oops. Okay, so you take this 17.4 kilojoules, convert it to joules since the unit's here are joules, and then we divide it by 100 and we divide it by 4.186. So the change in temperature of the water is going to be 41.6 degrees. Now, ask yourself, is that water getting hotter or colder? Well, the heat is released by this into the water, so the water is getting hotter by 41.6 degrees.